Good day. Today, we want to look at another limit of functions, which is referred to as limit at infinity. What we mean here when we say limit at infinity is that when the value of x becomes large, how does or what happens to the value of y? What we are saying is this: if you have the limit of a function f of x when x becomes large, either positive or negative, large, okay? So what happens to the value on the vertical axis? So let us start by first investigating the function f of x equal to x squared minus 1 all over x squared plus 1. So let's first see the way how this function behave graphically. So we want to represent this function graphically. So when we draw the graph of this function actually behave this way. Is how it behave. Okay, so this curve is the function f of x equal to x squared minus 1 divided by x squared plus 1. Okay, so if you plot the graph of this function across the real line, that is from negative infinity to positive infinity, okay, we see that this is how this function behave. So in this curve, we see that as x becomes large, the curve here is approaching 1. It's approaching 1, as you can see. So from the right and from the left, also if x goes to negative infinities, okay, we also see that the graph, which is a curve, approaches this line of 1, okay, and it does so, okay, till when we attain negative infinity from the left, and also this same when x tends to positive infinity from the right. So this simple situation can be simply be written as in terms of the limit form. We can write this as a form the limit when x tends to infinity, the function which is x squared minus 1 divided by x squared plus 1. What this means is that the limit of this is 1. As s tends to infinity, we have that the evaluating this tends to 1. And that's how it behaves when we draw the graph of this function. So that as s approaches positive infinity, okay, so the limit of this function is 1. So let us now give an intuitive definition of what limit of a function is when x becomes large. So now, definition. The function f of x is said to have a limit L, where L is a real number, about the point x tends to infinity if the limit of f of x as x tends to infinity is a real number. Okay, so this otherwise known as an horizontal asymptote. We'll discuss this later, though that as we have seen on the graph earlier, the line of this function form an asymptote with the point 1 on the vertical axis. As discussed in our last video, this limit at infinity also has some properties in addition to the limit at final value of x. So you will recall that we have discussed 10 limit properties under the limit at final value of x. So all the properties we'll be discussing here, okay, together with the previous one we have discussed, also hold for limit at infinity. So the properties, so this will be in addition to the limit at final value. So the last one we discussed is 10. So here we have 11. Here this says if f of x is equal to 1 over x, okay, then the limit of 1 over x as x tends to either positive or negative infinity, okay, so this is 0. Okay, let's come again. If you are given a function f of x equal to 1 over x, okay, so when finding the limit of such function 1 over x as x tends to either positive or negative infinity, okay, so the limit of this function is 0. So the 12th property is if you have a function f of x equal to 1 over x to the power of r, where r is positive, okay, again the limit of 1 over x to the power of r as x tends to either positive or negative infinity is also 0. Okay, so number 13, also if you have a function f of x equal to a constant raised to the power of 1 over x, okay, where c is a constant, okay, where c is a constant, then the limit of the constant raised to the power of 1 over x as x tends to either positive or negative infinity, this is equal to 1. Okay, so literally this limit will affect the power 1 over x, and of course this becomes 0. So by law of indices, c raised to the power of 0 is 1. So property 14. So this case a case of a special limit under limit at infinity. This states that if f of x is equal to x, then the limit of x when x tends to positive or negative infinity. Okay, this is equal to positive or negative infinity. Okay, in this case, we say the limit of this function does not exist. Okay, if answer is either infinity or negative infinity, okay, the limit does not exist. Also, 15, the second special case, this one says if f of x is x raised to the power of r, where r where r is positive, okay, then the limit of x raised to the power of r as x tends to either positive, okay, yeah, let's make it separate, okay, positive infinity, okay, so this will be positive, okay, so if the power here is positive, okay, and s tends to negative infinity, okay, so this will be positive infinity, so this will, the answer here will be positive, which means the limit does not exist. So one special case under this is that if you have the limit as x tends to negative infinity, okay, so the choice of the limit here will depend on the power here. So if this power is even, okay, so the limit will be infinity when r is even. When r is even, okay. Another case is this. So here, when this r is odd, okay, surely the limit here will be negative infinity. So in all these cases, I will say the limit does not exist if you have all these answers. So here, this is negative infinity if r is odd. Okay, so these limits we have discussed from property 11 to property 15 are limit order limit at infinity, in addition to the earlier one we discussed on limit at final value of x. Okay, so the limit property for limit at infinity now make it 15.